Using state-of-the-art large language models, we can take a natural language question such as the total profit per week for Q4 2025, and we can combine that with the schema of a database. We can pass both of these to a large language model, like so, and we can ask the large language model to write the SQL query that would answer our question using the given database. Now, this works really well if the database schema isn't too large, and also if the fields are well and unambiguously named. Unfortunately, in the real world, enterprise databases are extremely large and contain many fields that are poorly named and also contain abbreviations that are ambiguous. And as a result, the SQL response here is usually poor, unreliable, and inconsistent. We can deal with this problem by starting again and refining the information that we provide to the LLM before we ask it to write a SQL query. In this video, we're going to go through 3 of these pre-processing steps that we can go through before asking an LLM to write SQL. These 3 steps will increase the chance that the LLM writes the correct SQL, and to do so, we'll be using the Python library piglets. The first thing we can do is create a logical plan. One of the reasons we have this step is that we can perform this reasoning without the database schema, meaning that any negative influence the schema would have on the LLM's reasoning won't be present and it won't pollute the output. So let's use piglets first to create our logical plan. For the rest of this video, I'm going to be using an example that is in a Jupyter notebook which can be found inside the examples directory of the piglets repository. To find that, just go to github.com/importdata/piglets and then clone the repo locally if you want to follow along. So now that I've got a clone of the repo locally, I'm going to go into the examples directory and open the semantic linking example. And I'm just going to copy the additional dependencies from here. And I'm going to run this in the terminal to install them. This project uses the UV package manager, so you'll need that installed too. So now that that's installed, because we're inside the piglets project itself, we just need to alter the path so that we're able to import piglets. Next, we're going to set the model name to be GPT 5.2. Don't worry about the database type or the database path just yet. We'll come to that when we move on to the database. And we're also going to set the question to be which manufacturers saw the largest increase in average revenue per order between 1996 and 1997, considering only manufacturers with at least 100 orders in both years and excluding cancelled orders. So let's run that cell. And then let's just scroll past the create DuckDB database part. We'll come back to that soon. And let's go straight to step 1, create a logical plan. So here we're going to have the model verbalize its hypothesis without having access to the database schema. To do this, we import the logical planner from the piglets library. We initialize the logical planner with the model name, which is GPT 5.2, and then we call the plan method, and we pass the plan method our question, and then also we set the number of samples to be 3. Now, a logical plan is a sequence of steps that have to be taken to be able to get to the correct answer. And to ensure as many of the correct steps as possible are covered in our solution, we first ask the LLM to generate 3 logical plans and then to review all 3 plans and aggregate them into a final plan. So we're going to run that now. And now that's finished running, we can just run the next cell to inspect the outputs of our logical planner. So you can see here the first sample plan. Step 1 is to identify all of the order events and then the relevant values associated with them, such as revenue amounts, manufacturer, order date, and order status. Now you can already see here that sample plan 2 has a less thorough step 1. So step 1 for sample plan 2 doesn't include the order date and the order status. However, if we scroll down and look at the final aggregated logical plan, we can see that order date and order status are both included in step 1. And that's the advantage of generating several sample plans first before aggregating them into a final logical plan. And if you read through the rest of the steps, you'll see that these are the steps that we would have to take for any database when trying to answer the original natural language question. Now that we have our logical plan, the next thing we want to do is give our LLM the database schema. However, this is a large database schema that contains many irrelevant columns and also entire tables that aren't relevant to the question that we're trying to answer. These large schemas can also pollute the LLM's context, and it would be preferable to keep them to a minimum. So the next thing we're going to do is prune the database schema to produce a smaller pruned schema only containing fields that we believe to be relevant to the natural language question. Again, we're going to use piglets to prune the schema, but before we do that, we need to create our database. DuckDB is an in-process database. It's available in Python, and we can easily use it to create a sample database using the TPCH dataset. In this project, we've already created a function to do that for us. So we're just going to run this cell now to create a database for us locally. You can verify that this has worked by looking in the data directory inside the examples directory, and you can see this DuckDB file here which represents our TPCH database. And then now, if we scroll down, we want to go to step 2, where we first connect to the database and then retrieve the database schema as it currently is. To do that, we import the DuckDB URL class and also the database connector from piglets. The DuckDB URL class can be used to create a SQL Alchemy database connection string, which we pass here as the argument for our connection parameter. And then once we're connected to our database, we can use this method to retrieve the database schema. So let's run this cell. Now that that's finished running, we can inspect the existing database schema by running the next cell. Now, if we look at the current database schema, there are many tables. There's a customer table, which includes the customer key, the name, the address, the nation key, and so on. There's a line item table, which contains the orders. There is a nation table, which contains the dimensions associated with the nation key. There's an orders table, a parts table. Now, I'm not sure if this is a parts supply table or a supplementary parts table. And this is where the ambiguity of table and field names inside enterprise databases can lead LLMs astray when they're trying to create the correct SQL to answer a natural language question. We also have a region table and a supplier table, and they've all got multiple fields each. So the next thing we're going to do is prune our table schema so that it can be better used by an LLM to write the correct SQL query. When pruning our schema, we use an approach called dual pathway pruning. Dual pathway pruning first asks an LLM to create a deletion set. The deletion set only contains columns and fields that the LLM believe to be obviously irrelevant to the natural language question. Next, we ask the LLM to create a keep set, and the keep set contains tables and fields that might be relevant to the natural language question. Then, any fields that are in the deletion set but are not in the keep set are removed from the database schema. Luckily, we don't have to do those steps manually because the piglets library comes with its own database pruner that follows the dual pathway pruner approach. So let's run this cell, and notice we pass the dual pathway pruning approach our logical plan as well as our original natural language query. So in fact, the logical plan and the natural language question are both used to inform our schema pruning step. So now let's go back to the notebook and look at our pruned schema. You can see straight away that there are much less tables in the pruned schema. There's the line item table, the orders table, and the part table. Tables like the supplier table are irrelevant to our natural language query and would therefore be unnecessary information in our LLM's context. Now that we have a logical plan and the prune schema, we can use these together to create additional instructions that take into account the specific database that we're dealing with. This step is called semantic linking, and it's the final step of our pre-processing. So we're going to use the logical plan, the original natural language question, and the pruned schema to perform semantic linking. So to do this, we return to the notebook and import the semantic linker from piglets. We initialize the semantic linker with our model, and then we give the link method our natural language question the pruned database, and our logical plan. So let's run this cell. And now that's finished running, let's inspect the result by running the next cell. And as you can see, the semantic linking result contains schema-specific information and instructions that are going to be relevant when generating the SQL. This includes what the best date fields are likely to be able to restrict the query to 1996 versus 1997. It includes instructions on how to remove cancelled orders. And it even includes how you would use the line item table to be able to join the parts table to the orders table, and possible things to watch out for, such as conflicting grains causing duplicates in joins. The piglets library even includes a policies module, which can be used to determine how strict you would like the semantic linking step to be. And these semantic rules can be set for how we approach joins, grain, time, metrics, and ambiguity. And by default, they are standard for all, apart from ambiguity, which is 1. To demonstrate this, we can import the semantic rules class and also the rule mode class. And then we're just going to use those to create our semantic rules. So we're going to say our semantic rules are going to be the same as the defaults. However, the joins are going to be rule mode aggressive. And then we're just going to take these semantic rules and we're just going to pass them to our semantic linker like so, and then we're going to rerun this cell. Now that that's run, let's investigate the response and see if it has taken a more cautious and thorough approach to joins. And as you can see, joins are mentioned regularly and thoroughly throughout our semantic linking result. So now we've used our natural language question and the database schema to produce concise but thorough information that our LLM can use to create the SQL query we need to answer our natural language question. Thanks for watching, and if you like this video, don't forget to subscribe and also check out the other videos on Text-to-SQL and DuckDB on the channel page. Thank you.